Once again, welcome back. Let's take a look at the rest of this lesson here. We were talking about looking at key performance indicators for storage as they relate to I/O operations per second as well as with data rate, but another very important key metric is latency. As I was saying earlier, this is a great way to learn where the problems might be lying in your storage infrastructure since there's a lot of layers here. But with ESX top latency metrics, they can tell you whether or not is the problem a vSphere admin's problem because it's in the ESXi server, or is the problem outside of the ESX server. So it's the storage team's problem. And if you are responsible for both, well, then I guess you'll just have to change the hats, right, from one to the other. But in any case, thinking of the entire I/O trip, right, from the guest OS through the VM kernel, then through the storage infrastructure, and finally down to the device. Well, you have these important levels of latency. There's time spent in the ESX kernel. That's called kernel average latency. That's really short, like less than 2 milliseconds. Shorter than that is the actual queuing level within the ESXi host. That is so small that it's really imperceivable to really notice. I mean, goodness, 2 milliseconds is pretty short at the kernel level. Anything greater than that, that's a problem in the ESX server. Meanwhile, the moment the I/O leaves the host and hits your physical storage network and your overall network, and then writes to the device or reads from the device, and then returns the acknowledgement back to the host, that entire round trip is known as device latency. Now that really all depends on what kind of storage you have. It's always been traditionally 25 milliseconds, should not exceed 25, but in some storage environments, that's 20 milliseconds is what it shouldn't exceed. In others, it shouldn't exceed 15 milliseconds. It depends on so many different factors on the speed of your network, the speed of your storage devices, but generally you need to be watching out for this. Anything over 15, you're already looking at going, this might be a little suspicious. Remember those metrics when we were talking about storage I/O control, right? Storage I/O control used to kick in and engage its enforcements on equalization when it was 30 milliseconds. That was the device latency that we were talking about. And now it no longer does that, right? Because 30 milliseconds is just too fixed for too many variables. And so we now use a whole other metric for storage I/O control, but that's another story. Storage DRS, if you remember that actually will cause a potential storage vMotion if a data store is having a historical average latency of 15 milliseconds. So, that's where we kind of have these numbers. You want to make sure your storage isn't exceeding these kinds of numbers at the device latency level. So again, that's a storage outside of ESX server issue. So we can measure these. Inside ESX top, you can look at all these different latencies from the adapter view, from the LUN view, and from the VM view. And it will break it down between device latency, kernel latency, and guest latency. Can't forget the guest latency too. Now, guest latency is the entire trip from the moment it is leaving the guest down to the device and back. And it's kind of the sum of all the different latencies. There's no fixed number there because that's too dependent on the guest on what the number should be. But we have the ballpark figures for the kernel latency and as well for device latency. Now, those numbers look pretty high, but that's the local disk, right? So local disks may not have the traditional cache. So those numbers are really applicable for when we say these kernel latencies and device latencies are for high speed, SAN type of infrastructure here. If it's just a regular, magnetic boot drive, then these may actually be not necessarily good numbers, but these may not be crazy. But that's what we're seeing in this particular example. Now, when it comes to latency, we also need to be monitoring our queuing, right? Now, the one report that shows queues is the LUN view, because it can look at the actual device, the LUN device, and what the queuing is at that level. You can find a number of I/O operations that are currently active on that device and how many I/O operations that are now queued on that device. So open up your LUN view with the letter U. That's on the bottom part of the screen, and that's really what we're focusing on. We can see each of our different LUNs, what their queue lengths are. Now, these are not proper LUNs. These are probably just virtual disks masquerading as LUNs because they're in our lab environment. So they usually are much, much larger queue lengths here, like in the thousands. But in any case, we get at our queue lengths here, and then how many items are currently actively being worked on that device and how many are queued. So we already tell this system, this device, is already under some queuing load at this moment. It would be interesting to see what the latencies are at this point. And the thing is, in our particular slide, the top view actually has nothing to do with the bottom view. right? Because they're showing us that we have nice low numbers here, right? We have low kernel latency, we have low device latency. You would expect that if you're having some point of queuing on the LUN side, that may start bumping up your device latency queue. And your device average latency. So that is something you want to be watching out for. Now, these are not related. So this is just normal latencies in the first example. And down here, we're seeing actual queuing at the device. It would be interesting to see what the latency values are. They got cut off. They're over here somewhere. But these pictures are kind of related. They're kind of opposite to each other. If you're finding and looking at latencies, right, here's a normal good latency, right? Low latency giving us high throughput, right? 135 megabytes per second isn't too bad. If, on the other hand, you'll note that if we have really high device latency, that's high, that will have a major impact on your throughput. So certainly that's what we're seeing here, right? We want to watch out for these kinds of things. And now we see here that this is high device latency. This is not a host problem. This is something going on in your storage infrastructure somewhere, right? Notice our kernel latencies are nothing here, right? All zeros. So this could be, and I remember the text is actually suggesting that maybe something has happened on the array. Maybe, for instance, that the cache on the array has been disabled. This could possibly happen if these caches are non-persistent, so they need to be backed by a battery, and so they have a UPS to protect all that. And so if the UPS fails, then there's no backup, and so then a lot of systems will automatically disable their cache at that point. And so that might be what we're doing here. If we're trying to do a lot of writing and there's no cache, then that's going to have a huge latency impact, and then that's of course going to have a negative impact on our write throughput. So, keeping track of our different metrics here, what ESX top columns reflect the physical storage device latency? Now, keep in mind, we're asking all the columns, right? So, device latency is included in the DAVG for sure, right? Because that's the D for device. Well, what else in this list would include device latency? Well, remember, the entire round trip is also recorded by the guest latency. So those are the two. And thinking back to our picture, right? Guest latency records everything from the moment it leaves the VM till the time it hits the device, and which is including the device average latency as well. By the way, you don't want to ever see overloaded storage, right? Here we found latencies probably were ignored and queuing built up on the array, and now we had some overloaded storage, and we're having some aborted commands. Now, aborted commands are actually not in the default screen. You have to open up the field selector, hit the letter L to add error statistics so that you can get the aborts. We don't want aborts. You want them to be 0. If you have aborts, your array is essentially overloaded at this point. Now, what if you have unexpected increase in I/O latency on your shared storage? Consolidated applications can share expensive physical resources like storage, and you might have situations where the I/O activity on shared storage access affects the performance of latency-sensitive applications. You might want to watch out for a very high number of I/O requests that are issued concurrently, right? You end up having this immediate bottleneck of a whole bunch of I/O requests issued at once, or operations like a backup operation in a VM. The I/O bandwidth of a shared storage device could be impacted. To resolve these situations, one simple fix is storage I/O control. It'll make sure that when you have these immediate high I/O concurrent I/O actions and operations, storage I/O control on that device will effectively balance the I/O across all the ESX servers trying to access that same device. In fact, with storage performance best practices, what we really want to achieve is to ensure we've configured each LUN with the storage characteristics and for applications and the VMs that are intended to use that LUN. Avoid oversubscribing storage paths and storage devices. Multipathing is great for avoiding single points of failure, increased bandwidth. Storage DRS and storage out control with traditional storage wherever possible. That would mean iSCSI, VMFS, NFS, right? Make sure those networks that are using iSCSI and NFS are isolated. If possible, physical separation, but if you're consolidating networks, then keep them separated out using VLANs. Try to postpone major storage maintenance until off-peak hours. This all has to do with things like LUN reservations. This is helped mitigated in many ways with the VAI offloading of LUN reservations. You want to eliminate all possible swapping to reduce the burden on your storage subsystem for sure, right? Because if you're running low on memory and causing swapping, that's going to hit storage, which is going to impact on the ability for other workloads to use the storage system. And your SAN configurations, make sure your IOs are spread across all the available paths. So again, round robin works really well in that situation. And you'd want to have, if you can, complementary workloads where that in the same LUN, you're not putting all the IO intensive workloads on the same LUN. You'll want to spread them around to different LUNs. And of course, if you're using traditional storage, something like storage DRS will create that balance for you. And of course, balance your best practices with the objectives of your organization. There's always pros and cons to all these things, so you'd have to justify why are you doing one thing one way, and you may not have an environment that is able to support a certain best practice. So in our storage monitoring lab, this is actually an interesting exercise. In this Linux 01 VM that we've been using for the CPU and the memory monitoring labs, this VM happens to have 3 virtual disks. It has an internal boot drive, which we're not going to watch at this point. It has another internal data drive. That's the second disk. That's on a data store called 11 gigabyte local. And then it has another virtual disk that's on the SAN. That's on the 11 gigabyte remote. That's on the iSCSI SAN. And so what we're going to do is we're going to run a stress testing tool called AIO Stress. It's an open source stress testing tool. It's a lot like Iometer for Windows. And scripts have been created for us that mimic different kinds of workloads. For instance, we have a script that's called logwrite. That basically mimics writing a log. It's kind of like writing sequential IO, right? Appending in a log. Whereas data write, that script is mimicking random IO. And so, we're basically going to do a couple things in this exercise. We're going to have you set up the storage, but notably just pay attention to the 2 different writing scripts, logwrite and data write, because they're different. One's random and one is sequential. We're going to compare how they write to the same storage. They're both going to the iSCSI storage. You'd assume the one that offers sequential IO, like logwrite, should be able to take advantage of things like write behind. That would help speed up things, where data write, since it's random, it has to spend more time on each of the different IO operations. The next thing you're going to do is compare 2 reading simulations. One called File Server 2, which is a random reader, like as if it was reading from a file server. And then File Server 1, it's doing random reading, but this one's coming from the local disk. So now we're going to compare 2 readers, but one is from the SAN and one is from a local disk. Now, the File Server 1 will actually have to write first because it needs to read from something. So it's actually going to write for a couple minutes. We can ignore that part of it. But then as soon as it starts reading, you take a look at the numbers. And the goal here is to basically monitor IO operations for all 4 of these different scripts. So our goal here is to set up the different tests, right? We'll measure the continuous sequential write activity and the continuous random activity, then the random read and the random read from local versus doing it from remote. And so we're basically doing 2 sets of comparisons. We're going to compare sequential writes with random writes. That's comparing task 2 with task 3. And you're going to compare random reads on the remote data center with random reads from the local data center, where that random reads from the local data center, you're going to kind of wait out the writing part first before you do the reading. And you probably wouldn't be too surprised how this one turns out. You probably will find that the sequential will probably provide higher numbers of IO operations than the random one, just because of it being able to take advantage of sequential IO's right behind capabilities. And comparing random reads from a remote compared to random reads from a local, you'd expect a local would be able to read faster just because of the shorter distance on a local disk. That's usually how this one works out. Not to say that that's always what's going to happen. Probably all depends on what's going on in the actual lab infrastructure at the time you are performing the lab exercise. But that's generally how it will turn out. So our goals of this lab or this lesson were to determine which disk metrics to monitor, looked at the key performance indicators, right, IOPS, throughput, and latencies, and identify those metrics inside ESX Top, and finally demonstrate how to monitor disk throughput. And this ends this module where we took a look at storage protocols, storage configuration, RAID levels, queuing, and VMFS configurations. They're all factors that affect storage performance. Disk throughput and latency are key metrics when monitoring storage performance. And if a storage device is experiencing command aborts, the cause of those aborts must be identified and corrected, because if you're finding aborts, you have an overloaded storage. We don't want to see any storage aborts. All right. Thank you, and we'll see you. Well, go ahead and do the lab exercise, and we'll see you in the next module.